1. All right, welcome to lesson 1.1 notes on parent functions and transformations. Our learning targets for the day are to identify families of functions. We'll talk about families. What does that mean? Describe the transformations of parent functions, which is kind of one of the big, probably the main idea of the lesson, and also describe combinations of transformations. So kind of all go hand in hand with families of functions and transformations of those parent functions. Okay, so a little bit of vocab here as we get going. Just the first part, identifying function families, functions that belong to the same family. Okay, share the same characteristics. Okay, we'll use some of this terminology, but linear graphs would be an example of a family. They're all lines. They share similar characteristics. What we would call the parent function is the most basic, the simplest function of that family. Okay, and then any other functions in that same family are transformations of that parent function. Okay, so we take and we transform it. We'll talk about the types of transformations that we're going to look at, but we do stuff to it. We flip it, we stretch it out, we slide it. So those are some of the different transformations that we'll look at. Okay, so that's basically what we're saying is we've got just different groups, kind of types of functions, and anything else as part of that family are transformations of that function. Okay, so let's actually take a look at some of these types here. This first one, okay, we'll kind of name them all first here. F of x equals 1 as far as a rule, the parent function there. That's what we would call a constant. All right, it's a line. You can see the blue graph here is a straight line, but it's a horizontal line. Okay, the slope is 0 on that line. It's one that we need to kind of know the name of, but we're mainly going to work with these next three here. The what we would call linear family, which is hopefully what we think of when we see a graph like this. It's a line with a slope. The slope of this line would be 1. Y equals mx plus b is kind of that old form that we're hopefully pretty comfortable with. Our slope here is 1. That's our parent function. The second one, or I'm sorry, the third one here is what we would call the family is absolute value. So that's the name of that family. Very different looking graph. It's really almost two separate lines with two different slopes. We need to think V, absolute value, the V in value. Think V shaped graph. All right, and our fourth family here is what we call quadratic. All right, so those are the names of the families, at least for now, we're going to be working with: linear, absolute value, quadratic. Let's talk a little bit about the domain and range. We'll use some of the notation here. What we need to think when we think domain is how far does this graph go to the left? Okay, and how far does this graph go to the right? Well, what do you mean? How far does it go to the left? I see an arrow on this graph pointing all the way to the left, and which indicates that this is going on forever. So forever to the left, the smallest number on this x-axis as we go continually to the left would be negative infinity, right? We've got negatives to this side, positives to this side. So negative infinity is kind of the cutoff, which isn't really a cutoff, but this goes on forever to the left, and then we get the same thing on to the right. This graph goes to the right until it reaches, and it never really reaches that positive infinity. Okay, so domain is left and right. Range, we need to be thinking low to high or down to up. Okay, so for range, definitely different. What is the lowest value that this graph has for an output? Okay, we can see here that f of x equals 1. What are all of the outputs of this graph? Every output of this graph is 1, right? So I'd have the point right here as 0, 1. This point could be 1, 1. This point could be 2, 1. This point could be 3, 1, negative 2, 1, negative 5, 1, and so on. But what's true about every one of those points? The output is always 1. So for us, notation-wise, we could say the range is of this graph is 1. Okay, there is no, that is the lowest value, and it's also the highest value. Okay. In a future lesson, we'll go over what this notation means as far as why did I decide to use brackets versus parentheses. For right now, basically, just a real quick is if we're including the number, if 1 is part of that set, we want to include it. We want to use brackets. Infinity is a little bit of an outlier because there is no actually ever getting to negative infinity. So we're kind of saying we're not really including it. That's why we're using a parenthesis. Okay. Let's go to the second one here as far as domain and range goes. So domain, same idea. Domain is left and right. Okay, so how far left does this graph go? It's going, all we're thinking is left. So it is going to the left forever and ever and ever. If I were to extend this line, this would continue to go down, 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 and left, 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 left. So just like the first function, okay, I have a domain that goes from negative infinity, forever left, and just like before, it goes to the right forever. This would continue to go right, 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 right. Okay. Unlike the first graph, when I start talking about down and up, this graph does go actually down, 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 down. The smallest value that this graph ever has would be negative infinity. So this ends up with a range of negative infinity, and we're also seeing an example of going up, 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 forever to positive infinity. So two different functions with two different ranges. Let's change colors here. For our domain and range of our third, our absolute value parent function, okay, same concept, left. Okay, and we need to continue to go over it. This graph is going to the left forever, which we call negative infinity, and it's going to the right forever, to positive infinity, left and right. This way forever, this way forever. Range also is different than the first two. When I start to talk about what is the lowest y value or the smallest y value of this graph, it's going down. It stops when the y value is 0. Okay, that's the smallest. There are no negative values for this function. Okay, is there a maximum value? No. Well, we're approaching infinity. This graph will continue to go up, up, up forever. So we would say that this has a range of 0, including 0. That's why I'm using the bracket of 0 all the way up to positive infinity. Okay, let's do one more here. Our last one is very similar to what we just did for our absolute value, our quadratic parent function. Okay, domain, this is going to continue to go left, 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 left forever. We're talking this way, it's going to the left. Okay, so we're talking, whoops, I forgot my parenthesis on this one. We're going to the left forever, and we're also going to the right forever. Okay. Similarly, what's the lowest value of this graph? It's this point right here, like up and down we're talking now. So this graph goes down, down, down until it reaches this spot right here, and then it stops at that point. What's the value of that point? What's the output value? 0. The y value right there is 0. Okay. As far as going up, we're seeing the same thing as before. Both of these branches would continue to go up, 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 up forever. So we end up with a range of 0 to infinity. I know that's a lot going on there as far as domain and range. Double check your future lesson here, or stay tuned for future lesson as we go a little bit more in depth into domain and range components. Okay, so there's a look at parent functions, their names, the vocab that goes with them: constant, linear, absolute value, quadratic, as well as what their graphs look like. Okay, of the parent functions and what are their domains and ranges. Okay, so tracing this back, we've identified parent functions and what they look like. Hopefully now we should be able to check off, identify families of functions. I could show you a graph, and I would hope you'd be able to say, hey, that's a linear function, that's a quadratic function, that's an absolute value function. The next thing we got to do is be able to describe transformations. So we're going to take those parent functions and transform them, do something with them. These were kind of boring, right? They were just kind of, and that's kind of what parent functions are. They're as basic as you can get. So there's really, I guess 3 or 4, however you want to kind of classify, different ways that will transform these. So again, let's do the vocab. Let's kind of talk about this here, and then we'll bring it all together and see what that looks like on some examples. So a transformation. That's, I said it earlier, is our way of changing the size, the shape, the position. Okay, so size would be an example of getting bigger, getting smaller, the shape. Okay, as far as how it's, is it a V? Does it look like a V, or does it look like an upside down V? That would also maybe fall into the orientation of how it was orientated. Is it opening up? Is it opening down? But the position as well. Are we sliding it left, right, up, down? Okay, so that slide is actually, let's see, a translation. Let's see if we can squeeze it in here. A translation, that's kind of the official term that we would use for sliding, or a shift that shifts a graph horizontally, vertically, or both. Okay, but it doesn't change the size, shape, or orientation. It keeps it in its original form. Okay, we'll revisit here what this looks like in a little bit, but right now we're just making the connection. Translation means shift. Transformation, or I'm sorry, a reflection is a transformation that essentially flips. Okay, I think hopefully we're comfortable with that idea of reflecting something. Reflects a graph in this case over a line called, go figure, the line of reflection. And then basically at every point that we reflect over that line has to be the same distance from that line as the original point, but it's just on the opposite side of the line. So a quick sketch would be if this was my line of reflection, I could take this point, reflect it over it. It ends up right over here as the same distance from here to here, just on the opposite side. Okay. Our last one, that last type that we're going to work with here, last type of transformation, it gets a little bit, because we start throwing some numbers here into it, but it's basically multiplying all the outputs by the same factor. Whoops. Multiplying all the outputs by the same factor. Positive factor, sorry, other than 1. 1's not going to help us. If I multiply an output of 5 and I multiply it by 1, I'm going to stay at 5. So that's not going to help us. 0 would clear everything. So we're really just looking at positive numbers other than 1. Okay. When the factor that we multiply is actually greater than 1, The transformation is called a vertical stretch. Okay, so whatever graph we're looking at, if it's an absolute value graph in my parent function, looks like this, and we multiply all the outputs, we multiply this output, and we multiply them all by 3, or I'm just picking a positive, I'm picking a number greater than 1, that's going to cause this graph to get stretched vertically, kind of get taller and skinnier. All right. What other type of positive numbers do we have? We said greater than 1. Well, we can't do negative because that's not positive. We've got a whole set of numbers that end up falling that's greater than 0, but less than 1. Basically a number that's between 0 and 1, a fraction, a decimal that falls between 0 and 1. That's going to cause a vertical shrink. Vertical shrink. Okay, similar to above, but instead of stretching and getting taller and skinnier, so instead of going from that's maybe that same parent function here, we multiply all these inputs by half, it's going to cut that graph down and make it kind of flatter, one way to say it, or wider. Vertical shrink, it pushed it down. So there's a lot going on there, different transformations, different things we're doing. Let's put it all together, okay? This is kind of our last note as far as, and it's a summary really of all those transformations, okay? Really, and it's really just going to look at those 3, our linear, let's just put our names up here so we don't forget, our linear, I'm just going to abbreviate, absolute value, and our quadratic. Okay, so those are our families that we're really going to work with. This kind of ties into the multiple, but we're going to do it all right now. Okay, what could happen to this, to any one of these? There's really, like I said, 3 or 4 different things that could happen. This could become, let's just say f of x opposite of a times x minus h plus k. Kind of got. Okay, so what did I do? I've taken this x and I've done stuff to it. I've potentially multiplied it by, I've potentially subtracted h from it. I've potentially multiplied that by a. I've potentially multiplied that by -1. And then I've potentially added k to that whole thing. What are you talking about, Mr. Crow? All these a's and x's and h's and k's. Those just represent the different things that we could do to a function. Okay, we could do the same thing to both our absolute value and our quadratic. This could become, by applying a bunch of transformations or a series or 1 or 2, we can multiply this function by some number, the opposite of some number. I could take the x, subtract or add some number to it, and on the end, add k to that whole function. Some number, add or subtract some number to it. Let's see if we can squeeze in up here. That same thing, the absolute value and quadratic are very similar in the sense that we could kind of do that same thing. Let's squeeze it in up here. H of x equals the opposite of a times x minus h squared plus k. So I'm trying to be consistent and use the same letters for all 3 functions to make it easier to see that it really doesn't matter the whether it's a linear, whether it's absolute value, whether it's quadratic, we can apply these same transformations. Let's talk about what each one of these do for us. So stay with me. Let's talk about this a. There's really 3 things to consider. If a is less than 0, aka what else would we say that? That it's negative. if a is less than 0, there will be a reflection over the x-axis. Okay. So in any one of these, am I saying that it's always negative like this? Does this always have to be negative? No. But if I do see a negative number kind of out in front of the function, it's an automatic. It's one of those black and whites. Hey, that's going to cause a reflection over the x-axis. All right. So that takes care of our reflection. That's what it would look like in a function if that leading kind of number is negative. What else could happen to a? Well, we just got done talking about our stretch and our shrink. Let's see. If a, really now let's take the negative out of it. If the absolute value of a, so just kind of the number, ignoring any minuses or any negative signs that might be there, just kind of forgetting about this, forget about that negative if it's there. I just want to know the actual number itself. If that number is greater than 1, there will be a vertical stretch by factor whatever that a is. Okay, so that's what it would look like as a vertical stretch. We'll go through all examples of every single one of these. I know it's a lot of kind of theoretical and a lot of letters here going on, but this will be a consistent thing that we look at throughout the whole year. Okay, so I need to, if a, let's do one more thing that could happen here. If a ends up being between 0 and 1, then that's going to cause our vertical shrink by a factor of that absolute value, again, of a. Okay, so that really takes care of just kind of that number out in front of the function. That takes care potentially of a reflection over the x-axis. And either or, you're never going to have both. You could have a vertical stretch or a vertical shrink or neither. All right, not every function has to get stretched or shrunk, but if there is a number here kind of out front, that's how we're going to evaluate. That's how we're going to know was it shrunk or stretched. Okay, let's look at these last two because they go hand in hand. We can get that off there, I think. Let's use a new color. What is H going to do for us? Okay, both H and K are going to take care of our shifting, our translations. Okay, H will actually translates left or right H units. This one's kind of tricky because it's opposite of what it looks like. And I'll show you what I mean by that. Let's do a little, just even like an example here. Example, let's say we have a function j of x equals the absolute value of x minus 3, and that's it, just something simple. So here's what I mean. Look, there's something being done here. It's kind of this negative 3 is taking the place of the h, in our above function here. Okay, there's something going on. X minus h, now it's a number 3. And we said h, translate, it shifts, it slides the graph left and right. So this I know is going to cause a shift, h units, 3 units, but is it left or is it right? Intuitively, I think a lot of us would look at this and say, well, it's -3, that should be left. -3 moves us left on a graph, but actually, what did we say? It's opposite. So this would be, we would say, as far as the actual transformation here, translated right 3 units. Okay, so that's tougher. That's one that we really have to kind of understand what's going on there, as far as that's going to be an opposite. K works out nicely in that, I guess nicely in that what we see is what we get. Whoops, I meant to switch colors there on us. Thought I could do green, maybe not. Anyways, K, it's going to translate us, but where else could we go? Not left or right. Translates up or down. Okay, and we'll just say by this one that this one is actually true. And by true, I mean, like I said before, what you see is what you get. Okay, so now there's being something added on the back end of any one of these. So as I look at this, we could say, as just like a little mini example, I've got some function m of x equals x plus 2, a linear function, our linear parent function. If I were to take this off here, it's just linear, m of x equals x, but then plus 2, that's going to cause a translation. So we'd say translated up, because it's positive. Positive, you would think up and down, positive up, down would be negative, and that's exactly what we mean by true. Translated up 2 units. Okay, so that's a lot thrown at you right there. A, doing potentially 2 things for us, either a reflection and or a stretch or shrink, a translation up or down, left or right, based on whatever we have, H or K. Okay, this is kind of a, like I said earlier, a year-long theme for us. This isn't the only time we're going to do this, but this might be a section that you come back and rewatch, add to your notes, make notes on your notes type of thing. So let's take a look at what I'm asking you to do. I know we're kind of getting longer on the video, but that's just the way it goes. All right, so kind of going to our first 2 ideas here of being able to identify a family of functions and then also describe those transformations using terms like it's translated left, it's reflected over the x-axis, it's vertical stretch, it's a vertical shrink. So how do we do that? Let's take a look. That's kind of what we have left here, is just really either given a graph, can I do that? So identify the family. There's 2 different ways to do that. I can look, if I have the graph, I can look at the graph and see, what did Mr. Kroll say earlier? I see a V, I need to think absolute value. Okay, so there's 2 ways I could do that. Identify the function family. I can look at the graph itself and say, hey, that's a V, absolute value. I could also, in one like this, look at the function itself, f of x equals 2 times the absolute value of x plus 1, and just see, hey, there is an absolute value. This isn't a trick question. Our family is absolute value. And you can abbreviate like I'm doing. Absolute value. There's no tricks there. What's it going to be? It's going to be a linear, an absolute value, or quadratic. This is the part that I think is a little bit tougher, our comparison. Okay, so it's basically asking me to compare this graph to the parent function. We don't have to graph it. You know, the parent function would be on here somewhere. like this. But I almost think that I don't know, could be deceiving. So I'm going to take it off there and just look at the actual function itself. 2 times the absolute value of x plus 1. And I'm going to kind of flip back and forth here to kind of show where this is coming from. Let's talk about this 2, this number in front of the absolute value. Where did we see that? We said that falls in line with our a, right? A number in front of our absolute value. Is our 2 negative? Nope, it's positive. Okay, so that means that there is, I would never say anything about a reflection over the x-axis because a is not negative, it's positive. So this one's off the table. It is a number though. Is it greater than 1 or is it between 0 and 1? Well, I look at this and see 2 as being greater than 1. So that's an example. One thing I would want to say is a vertical stretch by a factor of 2. Okay, everything is basically twice the output that it was of the parent function. There's a second comparison to be made here. So this is kind of 1. I've got another number on the back end. Is it being directly added to the x, or is it on the end of the function? So let's take a look at where does that align here. I would say that plus 1 is kind of falling on the back end and saying, okay, that falls with our k. And so for now, I'm just using my notes and going, what does k do for us? I got to scroll down. K translates up or down, and it's the true one. What I see is what I get. If it says plus 2, we're going up 2. If it says minus 5, we're going down 5. So I see this one as plus 1. That means we're going up 1. Our vertex was originally here. Now it's up here. Okay, so I need to say that. I need to say that there is a translation or translated up 2 units. Okay, so we kind of customize a little bit. We say what it was a translation, but then where? Left, right, up, down. Up by how far? 2 units. Okay, so that's how we're going to use that big long note slide that we just made. All right, let's try it again. Different family. All right, all sorts of stuff going on here. Fraction, it looks scary. Same exact set of directions. For our family, you have 2 different ways. We didn't talk about it, and we'll have a whole chapter, or a whole chapter dedicated to this family. It's called a quadratic. Okay, I can tell that because of the shape. Is this a V? Not quite. Right? It's got a little curve to it. Is it a straight line? Definitely not. So it's not linear. It's not absolute value. This is called a parabola, like I said, which we'll cover in detail in future chapters. But the other way to look at it is to see here and say, oh, yeah, that's right. There's a squared going on. Okay, so I flip back in my notes and say, yep, there's a squared going on. That's our quadratic. Okay, family, quadratic. Great. Now the compare part. It's tougher. I don't need to see the parent function. I can get everything right off these numbers. So I see a 1/4 and I see a 3. The squared is just part of the function. Okay, the 1/4, where is it? It's kind of, where is it located? It's located in front of the function. So I go back to my notes and I say, all right, that number in front, here's my quadratic one. Oh, A, is it positive? Yep, it was positive 1/4. It was just, so I'm not saying this again, it's not a reflection, but it's a positive 1/4. So is that number greater than 1? No, it's 1/4 is between 0 and 1. So this is going to cause a vertical shrink by a factor of 1/4. Okay. Let's just say it. Vertical shrink factor 1/4. Okay, so I can almost check these off. All right, I checked that off. I said something about that. I didn't say anything about a reflection because there is no negative number. Is there a vertical shift? Is this going up or down? Nope. There's nothing being added here after the fact. I do see something being done to this x inside the parentheses. Let's go back and look. All right, that's the h, x minus h. We kind of did one very similar to this. We did it with absolute value, but h is going to take us left and right, h units, but this is the one that's tricky. It's the opposite one, and it's, like I said, it's actually the same number as we saw before. It looks like -3. That actually took us to the right 3 units. So nothing changes here for us. This x minus 3 takes us, our second transformation is a translated, let's use that term, don't say slide or slid or shifted, let's say it's translated right. So we get we get the vocab word, we get the direction, and then we get how far? 3 units. Okay, we can do those. All right, a little bit more here. Maybe we'll just do one of these. The other thing we could do is maybe you make your own graph. Okay, so you can see I've got some set up here where you're doing this. I definitely want to do an absolute value one, just because I know it's been a while since some of us have done that. These are all pretty good, so we might end up going through and just so you can kind of skip through and do take what you need from each one. So similar set of directions. It goes with our second. I can describe transformations of parent functions. Okay, I can identify its family. I know this is linear because there's no weird stuff. There's no absolute value. There's no squared. This is a linear family. Graph this and its parent. Let's start with the parent. We will talk more about this notation, this g of x. And I know I've been using it, so it's kind of weird to go back and talk about it now. This is no different than just saying this is the output. Okay, which traditionally we would think of as y. Okay, so this reads exactly as y equals x minus 4. So I'm hoping at this level we would be able to graph that. When in doubt, if you're ever stuck on a graph, you can always make a table of values, pick x values. Here's my input for x, input x values, see what you get for y. This would also be one that we could use our old friend, our form y equals mx plus b. Okay, and look at my slope. For us, we end up with a slope of 1 and a y-intercept, right? B is your y-intercept of -4. So that's probably how I would choose to graph this one. I'm comfortable with the slope-intercept form and just saying, hey, you know what? I see a -4. That means I'm going to have a y-intercept b of -4. And I can use my old school rise over run to go up 1 unit. Let's see, where are we at? Up 1 unit, over 1 unit. Up 1 unit, over 1 unit. Up 1 over 1. Just kind of old school graph, and y equals mx plus b. It was linear. Great. Otherwise, make a table of values. That's kind of all we're doing right now, is just reviewing graphing. What's the parent function? So here's where you might need to look back at your notes. The closest one I think we have was right here, and said, oh yeah, that was my linear parent function, f of x equals x. And I know sometimes people actually struggle with that one. So let's take a look. That would be like graphing y equals x. This is our parent. Y equals x. So how that ends up looking is your x and y values are the same. If I'm making a table, if I input a 1 for x, what does y have to equal? 1. If I input a 2 for x, what does y have to equal? 2. And so on and so on and so on. So I'd have 1, 1, 2, 2, 0, 0, -1, -1. So my parent function ends up right here. You could also take the same approach as before and say, you know what, I'm pretty good with this stuff. I realize that there's a 1 for a slope here, and there's a +0 going on back this way. So y equals mx plus b, y equals m, which is 1, x plus 0. I have a y-intercept of 0 with a slope of 1. So there we go. I've done this first one. I've graphed this and its parent function, then described the transformation. Well, hopefully at this point, this is kind of old school. We did it a couple different times in this last one. I could have actually answered this right away. I see this x and then being a -4. Now, linear can be a little bit tricky. is this, excuse me, is this going down 4? Or is this going to the right 4? Is this H or is this K? And if I look at it, I know on this one we had parentheses going on, but right now what we're looking at, there's no parentheses. So you could argue that, well, I don't know. I don't really know, Mr. Kroll. Is this left or down? It turns out it's actually either one. I'm going to try to do this here without screwing this up, but I could take this. So what are our two options that we're kind of thinking about right now? We're thinking this is a translation. It's definitely a translation. Something's being added or subtracted. So a translation, but what are my choices? Either down 4, and I'm just going to put our second option. It's translation. Remember the opposite, the horizontal would be opposite. So it looks like left, but it's actually would be right 4. And we'll decide. So here's the deal. Let's take our parent function. What if I go down 4 units? Can I do it? I need to use this. 1, 2, 3, 4. Down's looking pretty darn good. Let's take a look, though, and I think you can probably see where this is going. Let's look at right 4. I'm basically taking this point that I'm hovering over and moving it 4 to the right. 1, 2, 3, 4. Holy cow. Either one would be acceptable. Don't say both, okay? I'll leave it up to you to kind of decide. So it's one of those. It still holds true to everything we just took right here. Is something being subtracted from the x? Sure. You could argue that, yep, there was a horizontal translation, right 4 units. It looked like -4, but that would have meant right. Or you could have argued that, hey, something was being just added at the back end, subtracted that, and that took us down 4 units. Okay, so the only really new thing that's going on with this other part of the lesson is just reviewing someone making some of these graphs. Okay, so let's do it. We might as well. We're here. We're long enough. You can skip around as needed. But let's graph both. P of x equals the opposite of x squared. Sorry, before I get too far ahead, let's label these. Anytime we end up with two different graphs on the same coordinate, we want to label them. That's part of why we're using this notation. So this is g of x right here. Where was our g of x? You can just put it right next to it. If we wanted to call our parent function, f of x, then I could just call this f of x. And that way we're able to easily identify our parent function and then our translated function. Okay, so we'll do the same thing here. Let's kind of maybe split it and do it this way. So p of x, which is the same thing as y, equals, I'm just rewriting it, and then we'll kind of split it, and then I've got, let's just call our parent function, let's just use f of x. What's our quadratic? This is quadratic. Hopefully no secrets there. I'm looking at it. I can see a squared. No doubt. It's a quadratic function. Okay. Let's start here maybe. Let's start with the parent function. That's an easier one. So just kind of starting with something a little bit more basic. Remember, this is like y equals x squared. Make a table of values. Okay. If x equals, let's start with 0. 0, I'm going to plug in a 0 here. 0 squared is 0. Okay, cool. Let's plug in a 1 here. Oops. 1 for x. All right, 1 times 1. That's 1 again. What's going on? This is weird. I need more points than that. Right now, it's just 0, 0, 0, and 1, 1. If I were to just graph those, I'm going to have a line, and that's no good. Let's plug in a 2 here for x. What happens when I go 2 times 2, or 2 squared? 2 squared is 4. So now this is changing. The 0.24 is over here. 1, 2, 1, 2, 3, 4 up here. Okay. What about negative numbers? We got to be a little bit careful here. -1 squared, that's like -1 times -1. That's actually +1. So -1, 1 is over here, and I'd end up with -2, which -2 times -2 is +4. So I end up, it's actually a symmetric graph. This is our parent function. Let's label it f of x. This other one, I think, I don't know. Whoops, that's not what I wanted. Y equals the opposite of x squared. Let's make our table of values, and let's talk about what's going on here, because this one's kind of tricky. If I plug in a 0, here's kind of, there's like a little bit of an order of operation. First, I have to go 0 times 0, which is 0, and then I have to take the result and make it negative. This gets applied second. Okay, it's really like -1 times x squared. Okay, so 0 times 0 is 0. I make that negative. Well, you can't have a negative, so that's just 0, 0. But here's where this shows up kind of weird now. If I plug in a 1 for x, 1 times 1 is 1. So I'm doing the squared portion of it first, just kind of ignoring this minus and saying 1 times 1 is 1. But then now I need to apply this negative. So -1 times 1 is -1. One more time with 2. 2 times 2 is 4. But then I need to take my result and multiply it by -1. Therefore, 2, -4. So it's a little bit weird. It's kind of like the difference between, well, maybe this will illustrate, -x squared versus -x squared. What's the difference? Well, here the -x squared is more like this. -1 times -1 is +1. Here, which we're going to do next, if I plug in a -1, it's -1 times -1. That's my x. X is -1. -1 times -1 is 1. But then I need to, secondly, as like a second step, take that result and multiply it by this -1 that's negative up front. It's like separate from the function. Okay, so we do end up back at -1, and then same thing with -2. -2 times -2 is 4, but then I need to make that its opposite, which is -4. So kind of it's a good review of some skills there. We go to plot them. Here's 0, 0. Here's 1, -1. Here's 2. Let's see, 2, 1, 2, 3, 4. Same thing, -1, -1, and then -2, 1, 2, 3, 4. I go to graph it, I label it, life is good, P of x. Last thing to do is to describe the transformation. And again, I'm going back to that same old slide of notes there. It's quadratic. I see something, the only number I see, other than the squared, which doesn't apply, it's just telling me the family, is this negative. But what number is that? We haven't seen that yet. That's the a, right? So if I look here with the quadratic, there's a negative number in front. It's a -a. What's the value of a? And the one we were just looking at? 1. Okay, so there's a couple things to kind of assess here. If a is negative, is a less than 0? Yeah, that's what's going on there. There's going to be a reflection over the x-axis. And not like surprisingly or not coincidentally, this parent function all of a sudden got flipped over the x-axis. So I definitely want to and need to say, as far as a comparison, a reflection over the x-axis. Okay. What else could a do for us? So there's an a going on here. It's negative. Is the absolute value of a greater than 1? A is 1. So it's not a stretch. Is it between 0 and 1? No, it's 1. It literally is 1. It's not a stretch. It's not a shrink. So it's a good example. I know all the ones we've been doing, actually this one didn't have a stretch or a shrink either. The a was 1 again, right? We wrote it a few different times. A was 1. So there is no stretch or shrink. That's the only comparison I should be making there. All right, we're almost done. We need to review. And the only one we're going to do here is this absolute value one, because I know not everybody's 100% on that. So that we've got g of x here. Let's do it one more time with our parent function being f of x. equals the absolute value of x. So here's the deal with this. I'm actually just going to get this stuff out of here so we have a little room to work. Okay. Absolute value, remember, is how far is a number away from 0. So I'm actually going to let's do the parent function. Let's graph that first. Well, let's change that. Y equals the absolute value of x. Okay. And when I go to make a table, x, y, just because I have a space here, but you'll see, and I'm gonna kind of strategically set my table up here. 0, if I input a 0, how far is 0 away from 0? 0 units. It is 0. It's not anywhere far from it. If I plug in a positive 1 for x, the absolute value of 1 equals 1. It's 1 unit away from 0. Here's the part that everybody forgets. What is the absolute value of negative 1? How far is negative 1 on a number line? Here's 0, here's 1, here's negative 1. This distance is the same as this distance, right? So the absolute value of negative 1 also equals 1. Okay, same thing applies for 2. Absolute value of 2 is 2. Absolute value of negative 2 is 2. So that's where that comes from. So x is, I've got 0, 0, 1, 1, 2, 2, 3, 3. This would continue. But on this side, we end up with negative 1, 1, negative 2, 2, negative 3, 3. So that's how we end up with, I know we kind of started there, and it's like, well, what's with this V graph? Well, here we go. That's how it shows up. That's what absolute value is how far is a number away from 0. Okay, let's label it. That's our f of x, our parent. Lastly, let's graph this one. So y equals 2 times the absolute value of x. It's kind of like the last one where there's an order of operations that I have to follow here. I have to find the absolute, I have to find the absolute value first. Just get that out of there. I have to find the absolute value first and then multiply that by 2. Okay, so let's do it. 0. If I input a 0, what's the absolute value of 0? It's 0. But then 0 times 2, it's just 0 again. Let's plug in a 1 here. The absolute value of 1 is 1. But then when I multiply that by 2, I get 2. If I plug in a 2, absolute value of 2 is 2. But then I multiply that, I get 2 times 2 is 4. So there's 2 steps going on here. You have to evaluate the absolute value first and multiply that result by 2. Okay. Negative 1 goes in. We do something to it. We find the absolute value, which is 1. And then I multiply that by 2. Oh, there's my 2. So it's very symmetric. It should be symmetric, at least for now, unless there was a translation. Plug in a negative 2. Negative 2 absolute value is positive 2, but then times 2 is 4. So I end up with all these points, 0, 0 still, that's still there, but then 1, 2, 2, 1, 2, 3, 4. And then same thing going on over here, negative 1, 2, and then negative 2, 1, 2, 3, 4. So my graph ends up looking like that, g of x. As far as our comparison, describe the transformation. We should know this one. Again, it's going back to that. I'll reference this one. Again, I guess I can't promise one last time, but it's a number in front. And it's an absolute value with a number in front. Is it negative? No, it's 2. It's positive 2. So there is no reflection. And that didn't show up in the graph, right? There was no reflection. Whoops, wrong one. They both stayed opening up, so there's no reflection. But it did what? It got taller and skinnier. It got stretched out. This number that was greater than 1, 2, caused a vertical stretch. Let me see if I can section this off here. Vertical stretch by a factor of 2. That's a lot. That's a long lesson, extremely long lesson. Keep in mind, I'm making these notes so that, obviously with the intent that you can skip around and look at different sections. We've already talked about this, but we obviously more than one, it covers kind of our third point, our big idea that, I definitely say we can describe these transformations, we can make the graphs, we can describe combinations. without even, this one has a graph for us, but we can describe combinations. Okay, the graphs here's kind of my my take on this. The graphs can be misleading. Let's read this together. Below is a graph of the functions g of x, which is right here, and its parent function f of x. So I know off the bat just by looking at either this right here and saying, oh, those are absolute value bars, or the shape of the graph, oh, those are v's, those are absolute values, that this is my parent function, right? It's the one that's kind of centered here, 0, 0, 1, 1, 2, 2, 3, 3. We just made it a second ago. This one, though, is like, oh, what the heck happened? It looks clearly like a reflection has taken place. I'm just totally going off visual. But then what happened? Did it get stretched? Did it get shrunk? I don't know. I'm just going to follow my rules. One last time. This will definitely be the last time. There's a negative. There's something going on here. There's something going on here. Okay? What do those do for us? It tells us that this right here caused a reflection over the x-axis. This right here, the one that's being done directly to the x, that's my h, which is opposite. It looks like it should be, that's our horizontal. It looks like it should be right, but it's actually left. So translated, and you know what? We can tie these both together. Let's say this, translated, because there's two different translations, right? They're both happening. I'm sorry, left 5 units, and what's our last one? We haven't addressed. This k, which we said is always true. -3 looks like down, so we'll say down 3 units. So there's an example of, like I said, you could argue 3 is a reflection. This graph went from opening up to opening down. And this point, if I just looked at one single point, went left 1, 2, 3. These scale must not be going by ones, but 1, 2, 3, 4, 5. And then it went down 1, 2, 3. Okay. So it shows up, it manifests on the actual graph itself. So there's lesson 1.1. Long lesson, but we're laying some groundwork for some stuff that's coming. So I would say we can definitely describe at this point any combinations of transformations. So there you go. There's your notes for lesson 1.1. We'll see you in upcoming lessons.